In a library in Jerusalem lies an intensely curious document. It was written about 300 years ago, and only a handful of scholars have ever examined it. The author was arguably the most important scientist of all time, a genius who uncovered the laws of physics that govern the entire cosmos, Sir Isaac Newton. The subject? Newton's calculation of the date the Bible said the world as we know it would end in the Battle of Armageddon, the year 2060.
If this calculation were correct, then we are close to the time of the end. That's exactly what this sort of calculation would point to.
When this document came to public attention recently, it was headline news. But why was Isaac Newton making this dire prediction?
We find it surprising that Newton sounds like a televangelist talking about the end of time. We only find it shocking because we've made Newton something that he's not. We've made Newton an irrationalist, enlightened image. That's just not Newton.
What these manuscripts reveal is a very different Newton than most people conceive of. This is a Newton who is not a cold, calculating scientist. This is revealing Newton in all his glory, warts and all, if you will.
So who was the real Isaac Newton? On a small farm in rural England called Woolsthorpe, the conflicted life of Isaac Newton began in 1642. That same year, the astronomer Galileo had died, and his work was still sending shockwaves through Europe. Galileo had risked his freedom by challenging the ancient belief held by the Catholic Church that the sun moved around the earth. Based not on faith but observation, he confirmed the earth was just one of several planets orbiting the sun. It was the dawn of the scientific revolution, an age when science and reason would redefine the world.
There was a sense of a whole new era. The very idea of having the empirical world answer our questions, that idea was taking hold in a way that had almost never done so before.
And from a young age, Newton was gripped by this new outlook. As a boy, he pored over a book called The Mysteries of Nature and Art, a manual for building mechanical contraptions and investigating the natural world.
He was preoccupied by the things that preoccupy physicists, by time and motion. So he made windmills, he made little boats, he flew kites that supposedly affrighted the locals. He tied candles to them and they were put up and they thought that they were comets.
But from the start, there was another side of Isaac Newton. His father died before he was born, and when he was just 3 years old, his mother remarried and moved away, leaving young Isaac behind with his grandparents. Newton later confessed to such rage that he wanted to burn his mother and stepfather in their house. And by the time he left home for Cambridge University, Newton had lived through 2 decades of violent political and social turmoil. A bloody civil war, the beheading of the king, and the restoration of the monarchy under Charles II in 1660. At Cambridge, Newton buried himself in his studies.
Truth is the offspring of silence and unbroken meditation.
He didn't go anywhere. I mean, he rarely traveled. He never went to the continent. He was that insular. I mean, he stayed in his rooms. He worked 7 days a week, 18 hours a day, and he pushed himself, drove himself. He had a library of his own that had about 1,600 or 1,800 volumes, but it was very much a world that came to him through printed matter or through manuscripts from others.
The decadent atmosphere of Cambridge was something the reclusive young Newton wanted no part of.
It was a time, particularly after the restoration of Charles II, it was a time of great fun and frolicking, and I think Newton would have been dismayed by many of the antics of his fellow students, drinking, going after bad young women in local villages.
To resist temptation, Newton drew up a plan that he'd stick to for the rest of his life.
The way to chastity is not to struggle directly with incontinent thoughts, but to avert she thoughts by some employment, or by reading, or meditating on other things, or by converse. For he that's always thinking of chastity will be always thinking of women.
He's a very silent, thoughtful young man who, I suppose, looks as though he's utterly tedious from the outside. But there's no evidence, I think, that anyone liked him at all, apart from his friend John Wickens.
John Wickens was another Cambridge student. He and Newton became roommates after both grew unhappy living with students who put pleasure before work.
They have a very peculiar relationship because Wickens is somebody who is of a higher status than Newton at Trinity and seems to have become Newton's amanuensis, i.e. his secretary, over the following 20 years. But they must have been very close. They lived in the same rooms for 20 years.
As a student, Newton devoured the latest scientific ideas. It was widely accepted by this time that the planets orbit the sun. But now the question was, how did the planets move? What held them in their orbits? The most popular theory came from the French philosopher René Descartes, who thought of the universe as a giant machine, like a clock. Descartes said everything, even the orbits of planets, could be explained simply as the physical interactions of parts of this machine. But Newton had trouble accepting this view of nature.
Newton's a very smart guy, and he became convinced that the only types of statements that are acceptable are ones which you could, to put it bluntly, test in the laboratory.
But just as Newton was probing the limits of Descartes, the plague struck England. Thousands died every week. The university closed, and Newton returned home to avoid infection. And it was here, in the apple orchard just outside the family home, that the legend of Isaac Newton was born.
The story, of course, is that he's lying in the garden there, and instead of thinking about girls, he's thinking about the moon and how it goes around the earth and so on. And an apple falls, and the story goes, bang, he suddenly has the idea that the same thing that's making the apple fall is what's holding the moon in its orbit.
Newton told this tale himself in his old age, claiming that with the fall of that apple, he realized that what held the planets in orbit was not a physical mechanism like Descartes' clockwork, but an invisible force he called gravity. And he was convinced that the force pulling apples down to Earth and keeping the moon in orbit around the Earth were one and the same. He stayed up late in the evening, calculating the strength of that force by the light of the fire. But when the numbers didn't quite work out, he put the idea aside. Or so the fable goes.
I doubt that an apple was what stimulated him to get the idea.
It's almost certainly an apocryphal story.
Yeah, I don't think it's even known whether it ever happened.
I'm extremely skeptical about the role of fruit in Newton's life.
But there is no doubt that the motion of objects like apples and the moon captivated Newton at this time. The Italian scientist Galileo had proved in a famous experiment on motion that all objects falling to Earth pick up speed or accelerate downwards at the same rate, regardless of their mass. And finding the average speed of a falling object was a straightforward process. For example, if you want to find the average speed of an apple falling from a tree, all you have to do is divide the distance the apple travels by the time it takes the apple to fall. But Newton was not satisfied with the average. What would be the speed of an apple which is constantly accelerating at every point along the way? What would the apple's velocity be halfway to the ground? To find out, you can measure the apple's average speed over smaller and smaller periods of time. The shorter the time interval, the closer you get to knowing the apple's speed at that moment. But to find its precise speed at a single instant, you have to reduce that time interval as close to zero as you can.
Newton invented a way to make that time interval infinitesimally small. What is infinitesimally small? That is smaller than any number that you can think of. It's not zero, but it is smaller than any number that you can think of.
For the first time, it was possible to calculate quantities that are constantly changing, like the speed of a falling apple at any particular moment, or how a planet's position changes over time. With this technique, Newton invented an entirely new branch of math called calculus.
And that changed all science, of course. The whole way of looking at the world changed because of calculus, yeah.
Calculus was a quantitative understanding of the way things change. Not just velocity, but in physics, in chemistry, even in populations. How fast is a population changing over time? This mathematical framework becomes the language in which modern science is formulated.
Today, calculus shows up everywhere, from analyzing the stock market to modeling global climate change.
By the time he was 22 years of age, working on the calculus at Woolsthorpe, he was the greatest mathematician the world had ever seen, and yet no one knew. Only Newton knew, and it was his secret.
This was a guy who adored computation of every kind. Among the things that you can see if you open his manuscripts, for instance, is there are places where you'll find he's calculated logarithms out to 50 places and things like that. Not because he needed it, but because he liked doing it. I mean, it was a pleasure to him to do that sort of thing.
And if that weren't enough, Newton overturned accepted wisdom about how colors are produced, performing an experiment on himself with a large needle, or bodkin.
I took a bodkin and put it between my eye and the bone, as near to the back side of my eye as I could. And pressing my eye with the end of it, so as to make the curvature in my eye, there appeared several white, dark, and coloured circles.
Fortunately, Newton found a safer way to investigate light and color, using a prism. From Aristotle to Descartes, scientists thought sunlight, or white light, was pure. Colors were produced by physically modifying white light, which they believed passing it through a prism did. But Newton decided to see for himself. Sending sunlight through a prism, he produced the spectrum of colors. And then he went one step further. He sent the red ray of light through a second prism. Instead of making a new color, it remained red. Newton concluded that white light is not pure, but a combination of all the colors of the rainbow.
He thought of the prism actually as a separator of the objects that are all in the original light. This was very hard for almost everybody to swallow, because it meant that when you're looking at white light, you're looking at something which has all the colors already in it. This seemed completely counterintuitive, and indeed, frankly, it's counterintuitive to most people today.
Only 25 years old, Newton had made some of the most stunning breakthroughs in the history of science. But he kept them almost entirely to himself, just as he had done with calculus. After the plague subsided, he returned to Cambridge, where he worked his way up to an appointment as the Lucasian Professor of Mathematics, the position held by Stephen Hawking today. Newton became known for his prematurely white hair and for his long-winded lectures on light.
That belongs to refractions, tacitly founding their demonstration on a certain physical hypothesis not well established. I judge it will not be unacceptable if I bring the principles of science to more strict examination.
The introverted Newton had little time for students, and they had little interest in him. Years later, one of Newton's laboratory assistants would recall,
"So few went to him, and fewer that understood him, that oftentimes he did, in a manner, for want of hearers, read to the walls."
But Newton's study of light was about to start a revolution. 50 years earlier, Galileo had built one of the first telescopes. It used glass lenses to gather light from distant objects and focus it for the observer. But this kind of telescope had a problem. Its lenses produced fringes of color around the edges of the objects being observed.
And that meant that the objects that you looked at always had this chromatic aberration. They always looked colored, even when the original object wasn't. And Newton began on the side to make some things with his own hands. And he designed a remarkably and radically different kind of telescope from anything that had been built before.
Newton realized that the edges of a lens behave like a prism, breaking white light into different colors as it passes through. So he abandoned lenses and substituted a mirror to gather and focus light from distant objects. And because the light never passed through a lens, it was free of color distortion. Newton's telescope was only 6 inches long, but Newton bragged that it could
magnifying about 40 times in diameter, which is more than any 6-foot tube can do. I've seen with it Jupiter, distinctly round, and his satellites.
It was an instrument that has left its impact on astronomy ever since. Our huge telescopes of today are built on this model. They're gigantic versions of this tiny little thing. These are the telescopes that sit on the top of the great mountain peaks. These are the telescopes that we launch into space to peer into the deepest parts of the visible universe.
Newton regarded his invention as just a toy, but a colleague took it to London, where it was shown off to King Charles II.
The effect that it had on Newton's contemporaries was immediate and dramatic. It brought Newton onto the world stage of science, and Newton became an overnight sensation.
Newton was elected a member of the Royal Society, a group of leading scientists in London. Most of them were awed by the whiz kid from Cambridge, and Newton was so delighted that he promised to send the Royal Society a paper he had written on his discovery that white light is made up of different colors. But members of the Royal Society had no idea that Newton was studying something far more mysterious than light by this time. His private notebooks reveal that the same year he became a professor at Cambridge, he bought 2 furnaces, an assortment of chemicals, and a strange set of books. Isaac Newton had become an alchemist. Alchemy is an ancient and secret practice with roots in the Middle East. By carrying out lengthy and complex chemical procedures, alchemists tried to produce a magical substance called the Philosopher's Stone. The Philosopher's Stone was so potent that even a small quantity was said to perform miracles, curing ailments, conferring immortality, and transforming ordinary metals like lead into pure gold.
In the 16th and 17th centuries, there were many, many people who came to courts in Europe and claimed that they possessed the Philosopher's Stone. And they were employed by nobles and princes throughout Europe to make gold.
In some instances, it was immensely profitable. You could milk a duke or prince of a substantial amount of money, no question. But if you got caught, it was extremely dangerous. We know that one of the customary punishments for defrocked alchemists, as it were, was to be hanged on a gilded scaffold. And sometimes they were forced to wear suits of tinsel as they were hanged to make it a public spectacle.
As Newton immersed himself in alchemy, his paper on light was igniting a firestorm in London. The job of evaluating Newton's ideas fell to another Royal Society member, Robert Hooke, who would become Newton's lifelong nemesis.
The paper got published, and Hooke wrote a report on this. And it's a peculiar report, because effectively speaking, what it says is, I accept all of Newton's experiments, but whatever is new in them I already did, and all of his claims about light are wrong.
For 4 years, Newton and his critics fought it out, with blow after blow published in the magazine of the Royal Society. The sensitive Newton was mortified.
Newton was allergic to criticism. I mean, really allergic. He went off the wall when people criticized him.
The problem for Newton was having anybody question what it was that he had done. He didn't want to tell anybody about it in the first place, but if he was forced to do it, you sure better believe what he said.
He cannot convince as many people as he wants that what he said is true. And that defeat, if you like to call it that, was very bitter for him. And by the mid-1670s, he's withdrawn completely from the international world of science.
Newton vowed he would never publish a scientific paper again. In the isolation of Cambridge, Newton threw himself into alchemy. Alchemy had been outlawed because the British government feared that frauds would debase the currency with fake gold. And for years, controversy has raged over why Isaac Newton took up alchemy. Even Newton's lab assistant was baffled.
What his aim might be, I was not able to penetrate into. But his pains, his diligence, as those times made me think, he aimed at something far beyond the reach of human art and industry.
In the past, many scholars dismissed Newton's alchemy as scientifically worthless. But now, they're taking a second look. To find out what Newton was really up to, Bill Newman has begun deciphering Newton's coded recipes and recreating alchemical experiments Newton did 300 years ago.
If we want to figure out what's going on in these laboratory notebooks, that's the way to do it. Actually try the experiments and see what happens.
Newton believed that in the distant past, people knew great truths about nature and the universe. This wisdom was lost over time, but Newton thought it was hidden in Greek myths, which he interpreted as encoded alchemical recipes.
In some instances, he interprets the myths in a very, very exact way so that they correspond to actual recipes.
But getting these recipes right is no easy matter. Like all alchemists, Newton concealed his ingredients in bizarre-sounding terminology.
Our body, thus compounded, is called our hermaphrodite. Being of two sexes, and it is both father and mother to the stone.
He used a very colorful language that's typical of the alchemy of the time. For example, he talks about the green lion, the sordid whore, and the menstrual blood of the sordid whore. These are terms that had very specific reference in 17th century alchemy.
One of Newton's recipes, called the net, comes from the writings of the Roman poet Ovid. In his poem, The Metamorphoses, Ovid tells the story of the god Vulcan catching his wife, Venus, in bed with the god Mars. According to the myth, Vulcan made a fine metallic net and hung the lovers from the ceiling for all to see. In alchemy, Venus, Mars, and Vulcan mean copper, iron, and fire. Viewed this way, the myth becomes an alchemical recipe. And if Bill Newman has interpreted the recipe correctly, he should get the same results that Newton got 300 years ago. A purple alloy known as the net, which was believed to be one step towards the Philosopher's Stone.
Behold, the net. It worked. A purple alloy with a striated net-like surface. Worked perfectly.
By recreating these recipes, Bill Newman is finding that Newton's alchemy contained key elements of modern science. It was a systematic process with results that could be reproduced and verified. And historians have also discovered that Newton was not alone in pursuing alchemy. Other scientists of the day, including members of the Royal Society, were alchemists too. Perhaps Newton's alchemy was less an occult practice than another way to investigate the natural world.
Alchemy was really matter theory. Alchemy was a science which pursued the most basic questions of what is the earth, what is all of the universe made up of, what are the components of matter.
There was a profound element to the practice of alchemy which really makes it deserving of being called early modern chemistry. He's not a madman playing around with strange spirituous substances. He's trying to actually figure out how to change material particles around to get one thing out of something else, and that's not so weird.
Newton's alchemy came as a surprise when it was discovered in the papers bought by the economist John Maynard Keynes in 1936. But other manuscripts now housed in Jerusalem contained an even greater surprise. For most of his life, Newton held a dangerous secret. As a fellow at Trinity College, he was required to become a minister in the Church of England. But this was something he violently opposed. Newton became convinced that the central doctrine of Christianity, the Trinity, or the idea that Father, Son, and Holy Spirit were all equally divine, was not true. The more ancient Christian texts he read, the more he believed Christ was the Son of God, but not God's equal.
Now, because Newton was so convinced that God is extremely powerful and unique, Newton, as the saying goes, reads himself into heresy. In other words, Newton begins to minimize, to play down, eventually to deny the divinity of Christ.
And Newton comes to the conclusion very early on that the Trinity is a blasphemy on the first commandment, because the first commandment says that thou shalt have no other gods before me, and the worship of the Father, Son, and Holy Ghost, from Newton's point of view, is a heresy.
But denying the Trinity was illegal, and Newton was risking everything by holding these beliefs.
If Newton had been exposed while he was at Cambridge as an anti-Trinitarian, his career would have been over. He would have been ostracized. It's almost certain that it wouldn't have involved being put to death, but definitely prison would have been one possibility.
Newton was eventually excused from becoming a minister, but he wrote more about theology and alchemy than science and math combined. Only recently made available to the public at the National Library in Jerusalem, these documents are now revealing that for Newton, religion and science were inseparable, two parts of the same lifelong quest to understand the universe.
Newton himself wanted to design a universe in which God was absolutely present and absolutely powerful. There's an enormous irony there. In the 18th century, gangs of interpreters, most of them French, will take the God out of Newton's world. It's a very common image of what the Newtonian world was, that it was soulless, that it was mechanical, that it really wasn't theologically motivated at all.
Now, ironically, that's very anti-Newtonian, because Newton argued that God had to be present. You couldn't read him out of the universe.
The most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being.
Newton owned more than 30 Bibles, and he examined them as rigorously as he did the natural world. Correlating biblical passages with astronomical information, he redated ancient history, drawing up elaborate charts and chronologies that show civilization starting around 980 BC.
I have hundreds and hundreds of pages of computations and workings and reworkings where he tries to probe this over a period of close to 30 years. Time and time again, he'll come back to it, calculating and recalculating, trying to make it work just the way he tried to make his theories of light work.
With the same fervor that he brought to science and math, Newton also combed the Bible for keys to the future.
What he was trying to do is determine when the end would come, when Christ would return, when all the apocalyptic events of the end times would come to a head.
And that date is now alarmingly close. The year 2060.
Newton is not a man who keeps his theology in a box that he brings out only on Sundays, and then a man who does his science as a working man the rest of the week. Newton sees his work as a seamless unity, and his project is to understand the truth of God.
Most people today think of religion and science as completely different spheres. In Newton's day, science, the investigation of the natural world, was a part of religion. It was all questions in some ways ended in divine knowledge.
Alchemy and religion might have continued to dominate Newton's thoughts. But in his early 40s, he received a surprise visit that would refocus him on physics. It was the astronomer Edmund Halley, now known for the comet named after him. He asked Newton an esoteric-sounding question about planetary orbits.
My question is this. What kind of curve would be described by the planets, supposing the force of the attraction toward the Sun to be reciprocal to the square of the distance from it?
An ellipse.
An ellipse? How do you know?
I've done the calculation.
You have? How did you calculate it?
I'll show you. Should be here somewhere. Don't worry, I will redo the calculations. I'll send you a copy.
Halley's question would change science forever. Through years of observation, scientists had discovered that the planets move around the sun not in perfect circles, but in slightly elongated elliptical orbits. But no one could explain why. Halley and many other scientists had begun to suspect that the planets were attracted to the sun by some kind of force. They guessed that this attraction became weaker with distance in a mathematical relationship called the inverse square law. For example, the inverse square law says that if a planet is twice as far from the sun, the gravitational attraction it feels is 4 times weaker. But no one had been able to prove this resulted in elliptical orbits. Several months later, Halley received a paper from Newton. It was Newton's mathematical proof that a planet obeying the inverse square law of gravity must travel in an elliptical orbit. Newton may have used calculus to arrive at this, but he had not published this new form of math, and his proof was written in the traditional language of Euclidean geometry. But Newton wanted more than a mathematical proof. He wanted to know how the planets moved through space. For the next 18 months, Newton worked on this question day and night. He barely ate. He barely slept. And he saw no one.
When you look at what he did during that time, it's difficult to believe that any one human being carried out this amount of novel mathematical and mathematical physics research.
Finally, he submitted a 500-page draft of his masterpiece, the Principia Mathematica, to the Royal Society for publication.
It is the greatest book of science ever written, bar none. It is the most magnificent work. It is the most all-encompassing work. It is the most daring book of any scientific treatise ever written.
After the publication of the Principia, Newton is the man. I mean, you know, very few people can understand what this thing is about, but a lot of people can see there's something important in here.
What people saw was that Newton was providing a new framework for understanding the universe, building on centuries of work by his predecessors. Galileo had spent years studying motion on Earth and determined that projectiles always follow a curved path, called a parabola. But Galileo believed that motion of celestial objects, like the moon, was very different.
Galileo still believed that there were differences between the terrestrial and the celestial. He retained the idea that was ancient, that motion was different up at the moon and above.
Newton disagreed. He thought the same laws must govern motion on Earth and in the heavens. To demonstrate this, he would have to devise a set of laws so powerful they could explain motion everywhere. He began the Principia with a set of ground rules, his famous 3 laws of motion.
1.
An object in motion will remain in motion forever, unless acted on by an external force. An object's rate of acceleration is proportional to the force exerted on it. And for every action, there is an equal and opposite reaction. These laws allow scientists to make such accurate predictions about how objects move that they are still used today, to send rockets into space and explore other worlds. But explaining the orbits of the planets required another ingredient. This brought Newton back to the work he had begun 20 years earlier on gravity. To show how gravity works on Earth and in the skies, Newton designed a thought experiment. He imagined firing a cannon from the top of an extremely tall mountain. From his first law of motion, he knew the cannonball would travel in a straight line at a constant speed forever. But gravity pulls the ball downward. If its speed is low, the cannonball hits the Earth near the mountain. The higher the speed, the farther away the ball lands.
If you throw it faster, it comes farther away. Even faster, farther away. Even faster, it may go 1,000 miles. Even farther, it may actually go almost halfway around the Earth, and there hit the Earth.
Newton imagined that if its speed were high enough, the cannonball would travel all the way around the Earth and settle into orbit.
The orbit of the cannonball around the Earth was a balancing act between the cannonball's tendency to fly off in a straight line and its being yanked back towards the center of the Earth continuously by the force of gravity. So in Newton's picture of the world, there were 2 things. The natural tendency of an object to travel in a straight line, which was true on Earth or in space or anywhere, and there was the attraction of gravity, which was true on the surface of the Earth, and it was true up in space.
Newton's breakthrough was to see that the moon's orbit around the Earth and a cannonball's motion on Earth were governed by the same law of gravity.
That is a beautiful way of persuading you, me, and probably his colleagues that cannonballs falling to the Earth and the moon falling to the Earth is one and the same law of physics, gravity. The moment that he realized that, almost everything else follows from that.
Newton reasoned that if gravity governed motion on the Earth and the Moon, why not on Jupiter and its moons, which he had seen with his reflecting telescope? Why not the entire solar system? In a bold leap, Newton proclaimed that this invisible force operates everywhere in the universe.
It's an incredible leap. It's beyond anything anybody had imagined at the time.
Newton called it the universal law of gravitation, and he wrote it in one simple mathematical equation.
It's so important because it really tells us how nature operates in a fundamentally new way. Newton is saying the same thing that is going on in the heavens is going on Earth, and vice versa. It gives us a guidebook to answering the age-old question of what causes the rise and fall of the tides. It gives us answers to the orbits of the planets and their positions. It's a tremendous act of intellectual triumph, one of the great keystone, cornerstone pieces of our intellectual heritage.
It was a total revolution. The universal law of gravity was a complete revolution the way that we think about the world, the solar system, therefore the universe, whatever the size of the universe was in those days, and therefore the way we think about ourselves.
The Principia showed a promise that gravity by itself could account for virtually all the motions we know of in our planetary system. And the rest of science to this day has built off of that foundation. Newton turned out to be more correct about that than he could possibly have been confident of.
But Newton was not able to enjoy his success for long. As soon as the Principia was published, Newton's old rival, Robert Hooke, claimed he had come up with some of the key ideas first. And later, others attacked it because Newton did not explain what gravity is, just how to calculate its strength.
Newton himself didn't understand it. How can this object attract this object? There's nothing in between them.
That seemed to them as going back to some sort of an occult philosophy.
In fact, some think Newton's idea of gravity was related to the occult practice of alchemy. Newton was fascinated by an alchemical process called the vegetation of metals, in which inert metals seem to come to life and grow like plants. Today, we know this is just the reaction of mercury and silver with a solution of nitric acid. But Newton thought these kinds of reactions showed that mysterious, invisible forces he called active principles were at work everywhere in nature. Perhaps he thought of the invisible force of gravity in the same way.
Newton pursued alchemy because it gave insight into the active principles of nature. Gravity was an occult force. It didn't have an explanation, and Newton believed that it was possible that gravity was one of those forces, one of those active principles. And so, in that sense, Newton's alchemy could give insight into gravity.
Yet by the early 1690s, after more than 20 years of research, Newton's alchemical experiments had yielded no scientific breakthroughs like those he'd made in math and physics.
We're not quite sure exactly what he was trying to do. He certainly was looking for something. And, it's obviously something quite big, and he obviously did not find it because he opted not to publish anything about it.
I think there's no question that he was disappointed because he was looking for ultimate answers to questions. And he had failed in alchemy, as he had not failed in any other pursuit.
Finally, Newton had what many think was a nervous breakdown. He made wild accusations against his few friends, charging one, the philosopher John Locke, with trying to embroil him with women.
Locke is puzzled by the whole thing. What's up with Isaac there? He wasn't running a brothel on the side and bringing Sir Isaac to it.
When Newton explained that he was sick and had gone without sleep for 5 nights, his friends forgave him.
He was knackered. If he had a breakdown, I think it was probably because of exhaustion.
Whatever the cause, Newton's illness was brief. Within a few months, he seemed to have regained his composure. And soon, a strikingly different Isaac Newton began to take shape. Newton moved to London and was appointed Master of the Mint, a well-paid job that put him in charge of issuing new currency and cracking down on counterfeiters. About 24 counterfeiters were executed while Newton was in charge. Newton became a Member of Parliament, President of the Royal Society, and was knighted. He commissioned at least 14 portraits of himself.
It is an extraordinary change. He's very much this icon, and he settles into that role, I think, in London, and likes the role of the great man.
A year after Robert Hooke died, Newton published his second great masterpiece, Optics, which expanded on his work with light. At the end of this book, Newton finally wrote up some of his key ideas about calculus, 40 years after they were conceived. And although he had given up alchemy, he continued to devote himself to theology.
Right up to his death, he tried to keep his heresy as secret as possible. And he thinks, there's no point trying to convince these people of what I'm doing because the time is not right. These people aren't fit to receive the kind of word that I'm giving out.
Newton died in 1727. He was 84 years old. He was buried among kings and queens in Westminster Abbey, beneath a monument to his scientific achievements. His alchemy and passionate but heretical religious beliefs virtually unknown. Now, 2.5 centuries later, a new picture of Sir Isaac Newton is emerging, along with a new understanding of the roles that science, religion, and alchemy played in his life.
He sees his world as one world. He sees his pursuit of truth as one pursuit, and whether it takes him to books of theology or to books of nature, whether it be books of astronomy or books of alchemy, it doesn't matter to him.
What Newton does is brilliantly to use the tools appropriate to every field in which he worked. He's an ingenious and energetic builder who's astonishingly brilliant at composing gorgeous monuments of the most intensely clever design. Sometimes these appear as great books, like the Principia itself. Sometimes they appear in experiments, but we would be wrong to look for a single key which unlocks the whole mystery of Isaac Newton.
Man was a complete genius. I mean, people like Newton, if I shoot off the hip, maybe once in 500 years, at best.